Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome back to the deep dive. Today we are going deep, really deep into industrial microbiology and the complex engineering that goes with it.
We certainly are.
We're looking at a fundamental challenge in biotech and biomanufacturing. It's the journey from lab success to, well, industrial scale failure.
A very painful journey for many.
Think about it. You've spent months, maybe years, engineering this perfect microbe. It works flawlessly in a tiny 5-liter glass tank, right? Maximum yield, everything looks great.
The perfect run.
Exactly. But then you move that exact same process, same cells, same recipe, into a massive, say, 50 or 100 cubic meter steel reactor. And the performance just collapses.
It becomes completely erratic.
Wildly erratic. You get spectacular results one day and then total failure the next. So we've gone through a stack of sources looking at this exact gap, and the traditional approach, just scaling up, is clearly missing something.
Something big.
So our mission today is to understand why productivity collapses during this thing called scale translation. We're going to distill this idea that industrial feasibility isn't just about peak titer.
No, not at all.
It's defined by 3 things we have to treat as inseparable: productivity, variability, and the ability to scale. The core truth we're chasing is that industrial productivity isn't a measure of a cell's intrinsic potential. It's an emergent property of how well the biology and the engineering system are coupled.
That's the key.
Okay, let's unpack this.
That framing is so essential because it immediately forces us to stop thinking like, laboratory scientists and start thinking like industrial engineers.
Right.
In the lab, we are essentially running what our sources call the laboratory lie.
The laboratory lie. I love that. It perfectly captures the optimism of early R&D. So what assumptions are baked into that lie?
The lie is really the implicit assumption of perfection. We're operating in near homogeneous conditions, the temperature, the pH, the oxygen.
All perfect.
All controlled instantaneously. Disturbance is minimal and feedback is rapid and precise. And in that idealized setting, sure, metrics like peak titer do reflect the intrinsic cellular physiology, but the moment you hit manufacturing scale, that idealism is gone.
It vanishes.
The industrial reality is harsh. Productivity, as a number, only has meaning when you interpret it alongside variability and scale translation behavior.
Okay.
When processes become unstable or fail at large scale, we often look for, a genetic mutation or some big input error.
We blame the microbe.
You blame the microbe, but the failure is usually an outcome shaped by scale-dependent heterogeneity coupled with dynamic control system deficiencies.
So if that peak titer we get in the lab is, practically meaningless on its own, how should companies redefine success? What are the industrial KPIs that actually matter?
We have to move beyond just batch-level success. We
Right.
need to define productivity over the entire life of the process, so over time and across campaigns.
Makes sense.
The 3 key industrial KPIs, therefore, are, first, average campaign productivity. So the total product you deliver over, say, 20 or 30 runs.
The long view.
Second is batch-to-batch variability, usually quantified as the coefficient of variation, or CV, in titer. And critically, third, the frequency and severity of outlier runs those partial failures that just wreck your schedule.
That completely shifts the economic focus. I mean, you might have a process that can hit 100 grams per liter in theory.
Yeah.
But if it only hits that half the time, and the rest of the time it's down at 70 because of all this variability, it's a logistical nightmare.
It is, exactly. And that is the crucial insight. A process with, say, a 90 gram per liter average titer but tight variance and few failures is far more valuable economically than one that aims for 100 but is all over the place.
Because of the risk.
All the risk. Variability forces you to over-design your downstream processing, and it creates immense scheduling risk, inventory headaches. I mean, if you can't predict your output, you can't run a business.
So the engineers really have to be prioritizing operational resilience, not just pure biological output. This means industrial optimization becomes a trade-off.
Absolutely. The optimization target is a delicate balance between that biological potential and operational resilience. If you push the cells really aggressively, maximizing the growth rate with high feed rates, you can maximize short-term titer.
Sure.
But you dramatically reduce the system's robustness. You're narrowing the cell's tolerance window to any minor deviation in its environment.
Can you give us a concrete example of how that trade-off works in practice? How does choosing resilience over that peak number pay off?
Okay, let's imagine a process for, we'll call it compound X, an enzyme. The strain was optimized in the lab to hit a stunning 100 grams per liter in a small, perfect reactor.
Dream scenario.
The dream. When they scaled it up to 50 cubic meters, the process just became unstable. Small dips in dissolved oxygen, just caused by poor mixing, would instantly trigger the strain to shunt its carbon flux.
Meaning what exactly?
Meaning it diverted the feed away from compound X and into unwanted overflow metabolites like acetate.
So it starts making garbage instead of product.
Exactly, and it happened randomly. One run was 95, the next was 70. The solution wasn't better biology, it was reformulating the industrial objective. They accepted a lab target of 90 grams per liter,
Lore.
a slightly lower specific productivity, but they designed the process around a feeding strategy that was much more conservative and forgiving of those DO fluctuations.
And the result?
That robust, compromised process consistently delivered 85 grams per liter across all campaigns. That higher effective productivity over time, with low variance, was a massive economic win. They could actually plan production.
That really explains why consistency is so critical. So if inconsistency is the problem, where does it come from? We've talked about the cell's fragility, but our sources suggest the real culprit at scale is sitting right in the tank. It's just physics.
It is.
That transitions us perfectly. Biological variability exists, of course.
In expression stability, sure.
But when we jump to manufacturing scale, the source of performance variability shifts, and engineering-driven variability becomes, well, utterly dominant. The cell is fine, but its environment is hostile.
That's a great way to put it.
And here's where it gets really interesting. You're not dealing with a small, perfectly mixed container anymore. In a 100 cubic meter tank, you're dealing with massive challenges in fluid dynamics and mass transfer.
That's where you hit the gradient problem. Industrial vessels are, by necessity, non-ideally mixed. They exhibit gradients, so spatial zones of differing concentrations in DO, pH, substrate.
So a cell near the bottom, in the high shear, high oxygen area, is having a completely different day than a cell near the top or near the feed nozzle.
A completely different life, really. And we can break down the key engineering drivers of this variability into 3 factors. First is just incomplete mixing. You can't stir a huge tank fast enough to homogenize it instantly. So this creates spatial gradients, and as the cells circulate, they experience time-varying exposures. It's like a traveler on a very stressful roller coaster, cycling between feast and famine.
High oxygen, low oxygen.
Exactly. The second is oxygen transfer rate limitations, or OTR. Especially in these high cell density viscous broths, the physical ability to transfer oxygen from gas bubbles into the liquid, it just decreases.
That's the famous K-law.
That's the K-law. If the cells consume oxygen faster than the equipment can deliver it, you get huge vertical oxygen gradients. The cells starve.
Wait, let's just pause on K-law. Can you give us an analogy for what that is for someone new to this?
Sure. Think of it like this. K-law is the efficiency of the oxygen engine in the tank. If your cells are the cylinders in a car, OTR is the total horsepower.
No.
If the engine is dirty or the fuel lines, the bubbles are clogged, the K-law drops. Your cells might demand 100 horsepower to thrive, but the tank's physics might only allow for 80 horsepower delivery. That 20% deficit creates immediate stress.
Yeah, got it. And the third factor?
The third is control lag. The control system's resolution and its lag time determine how quickly a disturbance is corrected. The cell's metabolic response is measured in seconds.
Right.
If your control system takes 30 seconds to adjust the feed or oxygen flow, that 30-second delay is an eternity to a cell. It causes it to overshoot into all these undesirable metabolic states.
And these engineering non-idealities, they act as amplifiers.
Yeah.
They take a small thing, a slight difference in the inoculum, a tiny impurity, and blow it up into a major failure.
Precisely. We see this with starting conditions all the time. Take a generic fed batch process.
Right.
Runs inoculated with slightly older seed often show just subtly slower initial growth.
Oh, yeah.
But that shifted the timing of the peak oxygen uptake rate the moment the culture demanded the most oxygen. Since the feed profile was standardized, that timing mismatch meant the cells hit oxygen limitation earlier, and you'd instantly see more overflow metabolites.
Even though the recipe was identical.
Identical. The engineering context amplified a small biological difference into huge batch-to-batch variability.
This shift in focus is really the key takeaway here. We stop assuming the biology is the problem and realize the environment is variable and increasingly hostile.
That's right.
So let's tackle the methods engineers have historically used because they clearly haven't been enough to bridge this gap.
Right. And we need to distinguish between traditional scale-up and what we really should call scale translation.
What's the difference?
Traditional scale-up focuses narrowly on preserving specific average parameters, like power per volume or agitator tip speed. The logic is, if the average power input is the same, performance should be the same.
But it's not.
It's necessary for feasibility, but it is critically insufficient for predicting performance.
So why do these traditional methods fail?
They fail because they rely on those average measurements. They don't fully define the cellular exposure history in the large reactor. A cell is experiencing dynamic, time-varying environments that simply don't exist in the lab.
And there's a paradox here, right?
There is an inherent paradox. You can't preserve all the key engineering parameters simultaneously. For example, if you try to maintain a constant K, that oxygen engine efficiency, in a huge vessel, you might need incredibly high agitation speeds.
Which could damage the cells.
Exactly. The shear forces could go beyond the mechanical limits of the impeller, or, more importantly, the biological limits of a sensitive strain. Conversely, if you try to preserve a low tip speed to protect the cells, you often reduce your power per volume and lengthen the mixing time.
Which makes the gradients worse.
It increases the gradient amplitude, so you're stressing the cells chemically instead of mechanically.
So scale translation isn't about replication. It's about making a really difficult choice. Prioritizing which constraint the cell is least sensitive to.
That's it, exactly. Shear, oxygen limitations, substrate spikes, you have to pick your poison. If you fail to prioritize, you end up with a system where the organism is just unexpectedly pushed into a hostile regime.
And that hostility comes directly from those non-ideal mixing dynamics.
It does. I mean, these dynamic shifts impose dynamic metabolic responses. Consider how the cell experiences the tank. They face substrate spikes near the feed nozzle, which forces them into wasteful overflow metabolism.
Making more acetate.
And then they face transient oxygen depletion. As they circulate, they repeatedly pass through these low OTR zones. This cycling upregulates cellular stress pathways, which directly steals energy and reduces productivity.
So the organism isn't genetically unstable, it's just physiologically fragile when you expose it to these huge swings.
Right.
The misdiagnosis is often strain instability when the root cause is the environment.
That is absolutely correct. And the diagnostic tool that proves this is the scale-down model.
Ah, right.
We saw a case study in a large-scale enzyme process where productivity was just inexplicably low. So they set up these specialized scale-down bioreactors that intentionally imposed periodic DO oscillations.
So they simulated the roller coaster.
They literally programmed the oxygen to drop and rise cyclically, mimicking the cell's circulation pattern. And that simple simulation successfully reproduced the reduced specific activity they saw in the plant.
Wow.
It proved the root cause was gradient exposure, not strain evolution.
That is a phenomenal use of diagnostics, using engineering to diagnose an apparent biological failure. But the system's ability to collapse, it isn't a one-time thing, it's cumulative.
Yes.
Which brings us to a sobering fact. The problem doesn't just reset when you clean the tank. The entire facility retains a memory that can amplify this variability over time.
We're talking about campaign-level drift.
Exactly. Even if your recipe is the same, equipment condition, fouling, sensor aging, they all subtly shift the operating parameters under the surface. It pushes the system closer and closer to that physiological cliff edge.
They do, and these slow drifts lead to abrupt productivity failures when the cumulative change finally passes a biological tipping point. The facility's memory acts through several key amplification mechanisms.
Okay, what are they?
The first is heat transfer fouling. Over successive runs, scaling or biofilms build up on the heat exchange surfaces. This reduces the U value, which is just the efficiency of heat removal.
So it's harder to cool the tank.
Much harder. So it gets more difficult to pull heat out when the culture peaks. This can force the temperature to deviate slightly higher, which shifts the cell's metabolic rate and stress level.
So the controller thinks it's holding 37 degrees, but its ability to respond to a heat spike has been silently degraded.
Precisely. The second mechanism is mass transfer drift. Fouling of spargers or filters, the things that introduce air, can change the bubble size or reduce the effective area.
And that lowers the clealer.
It lowers the effective CLELA, so when that drops, the DO controller has to work much harder, or it just fails to maintain the oxygen level.
And finally, the instruments we rely on start lying to us.
That's sensor drift. pH and DO sensors are sterilized over and over with SIP cycles. This process progressively damages them. It increases their bias and their lag time.
Widening the gap between what you measure and what's real.
Exactly. If the controller thinks the pH is 7.0, but it's actually 7.2 because the sensor has drifted, it allows for these operational excursions that can push the culture right out of its optimal range.
And the scary part is how the biology interacts with all this accumulated drift. Because cultures are often operating right at their physiological limits.
Right at the edge of that perfect lab performance.
They respond nonlinearly to these small environmental changes.
That nonlinearity is what causes the abrupt collapse. A small, gradual decline in clough from a fouled sparger might cause a massive, seemingly abrupt drop in productivity because the culture suddenly hits a hard oxygen limitation threshold.
It's a slow-motion car crash.
That only becomes obvious when the cell hits a wall. This isn't strain evolution, it's cumulative environmental degradation.
Okay, so if the problem is environmental dynamics and facility constraints, the solution can't be to force the system to perfectly replicate an ideal lab environment. Physics just prevents that.
It does.
The solution must be to design the process, and maybe the strain, to tolerate the industrial chaos.
That is the new objective. Robust productivity requires designing processes to tolerate variability, rather than relying on the exact replication of ideal conditions. It means operating in a conservatively chosen window that deliberately avoids those steep, nonlinear response curves.
You sacrifice peak performance for resilience.
That's the trade.
So what are the actionable design principles that flow from this? How do we build that robustness in?
3 things really stand out. First, conservative margins. You have to ensure that your characterized OTR and heat removal capacities exceed the peak demands by a defined margin, say 20%, to account for that expected drift and fouling.
Build in a buffer.
Exactly. Second, conservative feeding. Use controlled profiles that avoid pushing cells into deep overflow regimes near the feed nozzle.
So you accept a longer batch time.
You accept a slightly longer batch time in exchange for robust, predictable yields across those mixing gradients. That extra 12 hours is a great trade-off for eliminating 2 failed runs a year.
And critically, the third principle means we have to fundamentally change how we use pilot studies.
Absolutely. Stress emulation. We have to stop using pilot and scale-down reactors just to confirm best-case performance.
Right.
We should use them intentionally to probe the vulnerability space. You introduce realistic gradients, you program in delays and feed correction, you restrict agitation, you test to see how productivity responds under manufacturing-like stress.
You're probing for robustness, not just confirming potential.
That's the major paradigm shift. We start blaming the organism and we start using diagnostics to ask the right questions.
Which are?
When productivity drops, diagnostics must prioritize asking if the environmental exposure has changed in ways not captured by those average set points. Has our peak oxygen demand exceeded our capacity? Has the substrate gradient increased? That's the first question, not is the strain stable.
So what does this all mean?
It means that productivity collapse during scale translation is generally rooted in environmental dynamics and facility constraints. Full stop.
And success requires deliberately prioritizing engineering parameters, like maintaining that OTR margin and accepting compromised conditions that maximize resilience over peak performance.
It's an integration problem, not a biology problem.
This has been a critical deep dive. I think the ultimate insight we've taken from these sources is that industrial productivity is the ultimate indicator of how well the biological potential and the engineered reality have been integrated.
Well said.
The aha moment for you, the listener, should be this. When you are evaluating any complex industrial process, tight variance often outweighs high peak performance. Resilience is the highest value metric.
Absolutely.
Thank you for joining us. This deep dive into managing inherent variability really sets the stage for advanced process analytics. If biological systems respond nonlinearly to small environmental changes, and we know the tank is heterogeneous, we're left with a final, provocative thought. What is the true impact of placing a single sensor in a non-representative zone of that tank? Should the operational goal be to measure the average state of the reactor, or should we instead be trying to specifically identify and mitigate the most stressful microenvironments the cell is actually experiencing? We'll leave you to chew on that one.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Ernala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.